So thanks everyone for signing on. Today's speaker is Markus Stabrin from Max Planck in Germany. He's a grad student in Stefan Rawson's group, and he's been working on the TranSPHIRE pipeline for automated cryo-EM processing, which is an area particularly close to my heart. So this seems like it's going to be a really interesting talk, and there's a lot of really cool ideas coming through in it. So personally, I'm really interested to see what he has to say. So with that, take it away, Markus.
Thank you very much, and thank you for offering me this opportunity to present my work. So I will present to you TranSPHIRE, an automated and feedback optimized on-the-fly processing tool for cryo-EM. And let's see if this works. So as a quick introduction, what does it do? So maybe I'm not sure if everybody is familiar with the field of cryo-EM and single particle analysis, but in the recent years, the hardware and software development in especially the data acquisition scheme led to a dramatic increase in throughput. So that means we now can collect thousands of images within a few days, while previously it was only a few hundred. So this means we create tons of data, but at the same time, this data does not necessarily mean to be the best data possible, especially because automation is usually a trade-off with quality. So what we are trying to do is that we get the most out of the data in a short amount of time while the data acquisition is still ongoing. So, which means that TranSPHIRE is running live next to the microscope, or is designed for this purpose, and it covers most of the common pre-processing steps. So on the right here, I guess here's actually you can go to some laser pointer maybe. I guess it's maybe better visible. So here on the right, this is kind of the standard single particle analysis pipeline. So we start from the microscope, we transfer our data to some station that we would like to work with. This could be either a cluster or a single workstation. Usually we compress our data, we want to back up the data. We do motion correction on our direct detector images, which I assume is the standard nowadays in the field. We do CTF estimation, which means we try to estimate the errors coming from our optical system so that we can correct for them later. We do particle picking, which means we identify the regions of interest on our micrographs, which we call particles. And this is done usually automatically. Then we do 2D classification to identify good and bad groups within our data. We do 2D class selection, which means that we separate manually, usually, that this is a good class average, this is a bad class averages. Bad class average can either be contamination, so for example ice or ethane contamination, or also a conformational state of a protein, or even a completely different protein that we don't want in our data right now. Then we create a 3D reconstruction. In our SPHIRE pipeline case, this is based on the 2D class averages because I have an improved signal-to-noise ratio compared to the original particles. And then we run basically the heart of the single particle analysis pipeline, which is the 3D refinement. And usually also there's heterogeneity analysis and local resolution estimation and filtering in order to enable model building and to improve the resolution. So TranSPHIRE covers most of the so-called pre-processing step, which is here in gray and blue or greenish, blue-greenish. But recently we also added the possibility for ab initio 3D reconstruction and 3D refinement when we added 2D clustering, and especially we developed Cinderella, which is our 2D class selection tool. And there was already a talk in an SBGrid about it, and Cryolo as well. So if you want, go check them out on, I guess they are available on YouTube. And recently, we also added the new feature, which is the automated data or processing optimization, which is here shown in purple, which is a feedback loop between particle picking, 2D clustering, 2D class selection, and feeding the information we got from our separation between good and bad class averages and the respective particles back into the training of the particle picking to get the maximum and good results. So TranSPHIRE itself is separated into three big different parts. The first is the GUI settings. So TranSPHIRE has a user-friendly interface, which is more or less looking like this GUI here. And everything is set up in this GUI. The next step is once we set up everything which is necessary for the session, we can click on Start here, and our processing starts, which means that it runs all the steps I just showed in the last slide, and just showed in the last slide in a parallel way so that it's optimized for speed. And finally, there's a GUI visualization. So that means every result that we get from every single step of the TranSPHIRE pipeline is visualized and can be assessed live on the fly during the data acquisition. So this allows us to find or identify possible problems of the data acquisition itself directly. Let me give you an example. For example, you collect a faceplate data set, because this is one of the most easiest examples. And when you collect a faceplate data set, you want to make sure that first you can estimate your CTF parameters, and second, that you have a phase shift development which is close to 90 degrees of phase shift, because this is like the optimum. So, however, if you just look at the raw images, you can't see which phase shift it is, and second, if you can estimate it in the first place. So when you have this live feedback, and you see with every incoming micrograph, like 5 or 10 seconds later, you see the estimated phase shift and the respective defocus values, you can also immediately say, this is perfectly fine, I want to collect here, or I want to switch position and of the position of the faceplate in order to optimize the data acquisition itself. And the same is true for example, drift or pick particles, because they are better or less good as squares. So you might want to optimize your data acquisition so that if you collect your 3000 micrographs within a session, those 3000 micrographs also have the quality that you need in order to reach a high resolution structure. So TranSPHIRE itself is designed to run on a single Linux workstation. It can also be a compute node on a cluster. It provides a user-friendly interface, and it's actually a wrapper for existing third-party programs. And the pipeline execution is highly parallelized so that it can reach the maximum speed on the workstation. So this wrapper for existing programs means that TranSPHIRE itself is basically a pipeline mechanism which chains all the programs in a way that it makes sense and is fast. So if you want to read more about information, you can check out the TranSPHIRE website and our publication, which is currently in press in Nature Communications, and the code is available on GitHub in case you want to check it out. So now I told you about what is TranSPHIRE. Now I would like to tell you how to use TranSPHIRE, because it might be very interesting for you to get an idea of how difficult is it, and so on. So first is TranSPHIRE needs to be run from the command line. So when you run TranSPHIRE in your command line after successful installation, it will tell you what the current version is. Here we have a version that is higher than the currently available version because it's on my development machine, but it will also tell you when there are new updates available. And you might want to check it out on the website if those updates affect your current workflow or not. And once the TranSPHIRE GUI opens, it will ask you if you want to restore your default values, yes or no, which leads sometimes to a bit of confusion. So most likely you always want to press yes if you want to start a new session, so that you don't load any settings by accident from previous session that you don't really want in your current session, or no if you want to continue your session because you need to stop it for some reason, or if you want to monitor your session. So it's possible to monitor a session from a different computer and start another TranSPHIRE instance, for example, just to get the visualization. So this is how the TranSPHIRE GUI looks like when it's opened. So we have here during installation, we have several mount points set up. So it allows you, after proper setup, to mount specific programs, mount points on the fly. For example, we have our backup server, which is called Billy, after the IKEA cupboard Billy for storage. So the user that comes to this computer, which is a shared computer, and everybody logs in with his or her own account, they mount the backup, they mount the computer of the camera that they use for data acquisition. We have three different microscopes with 4 different cameras, so it's always a different one. And we want to mount usually our cluster CLAM here, because there our data needs to be when we want to work with it. So this means we can here, no, this means, but we can basically separate our the GUI into 4 different parts. The red part is a notification area. So here you can set up, either in the beginning or during the TranSPHIRE run, you can set up receivers of the messages that TranSPHIRE sends. And the messages can either be sent via email or Telegram if it's set up. So this is communicating via a bot. So if it has any messages for you, like there are new class averages, this hole doesn't, or this square doesn't produce too many particles, or the drift is exceptionally high right now, then it will send the notifications to this checked users here. Then we have a general tab, so you can or the system administrator can set up templates that can be chosen from here. So you choose a template, and a lot of settings are pre-filled already. And you can click start or stop, or load or save your settings right now. Then we have the control area, which is where people spend most of their time in, because here you set up mount points, you set up settings. There's a retraining option to retrain Cinderella, and the visualization of the results. And finally, there's a status area. So once you click on start, here you see the current status, how many images have been processed, how many images are processed, how many need to be processed. So when we, after setting up a mount point, in case we want any, this is how you basically, how you use TranSPHIRE. So first we have the up up row of tabs. So here you just follow from left to right. So first you mount, then you go to settings. Every time you switch between tabs here, we have a second tab row, which is going from top to bottom, which is kind of what you're used to from, for example, I guess EPU is using kind of the same scheme. So we're going top to bottom here. And inside of each of those tabs here, we have another 3 tabs for clarity and user friendliness. Because let's say, in this case, we have 6 settings which are in the main tab and 1 which is in the rare tab. So if you're a beginner user, you usually don't want to touch the settings in the rare tab. So either I or the person that set up this the template made the decision for the user. This is a main tab setting, this is an advanced tab setting, or a rare tab setting. So it means if you stick to the main tab when you're new to the TranSPHIRE pipeline, basically that's what you want to do. And additionally, we have this icons here. So the folder icon opens a file open dialog, and this enlarge icon opens an enlarged view. So in case you have a very long file name and you want to see it as a whole file name, you can open it this way. So now, what is the input to TranSPHIRE? The TranSPHIRE supports several versions of data acquisition software. There is EPU, which is greater version 1.9. Luckily for us, EPU did not change for a long time now, but before 1.9 they kind of changed output file specifications a lot. So usually you don't want to use the old ones here, or I hope you don't use those anymore in your facilities. And that we also support Latitude S, which is the EPU version of the Gatan company. And it also supports Just Stack, which means if you get your data after data acquisition just on a hard drive from a facility, you can use the Just Stack option to run it through the TranSPHIRE pipeline. Not live in this case, but at least you can run through the pipeline to get your data processed, in case you don't have an already automated pipeline available, or you just want to redo it. It also comes, so every of those options also has a respective camera option. So the EPU output for K3 or K2 is different from an EPU option output of a Falcon 3. So it needs to know what kind of output to expect in this case. And it also expects a certain amount of input frame extensions so that it knows what to search for. Yes. So as you can see in this case, I say, okay, I want just a stack. It's a K2 camera, and with it's just stack, it doesn't actually matter what kind of camera it is. And then you can go into you see the input project path for frames is in this case the same as for the JPEGs. But this is not necessarily the case, unfortunately. But if you collected a data set yourself, you might know that there is if you specify something in EPU as an output directory, this is where the JPEGs are stored, and the frames are stored in a different directory, which is in the main directory. So you need to specify different paths in this case. And you can also provide the number of frames, so it will run a sanity check on every input file if the expected number of frames is actually met. So corrupted images do not make it inside the pipeline. So now I want to give you an overview of the kind of settings, what is TranSPHIRE doing, and what is and why do we have these gray areas, for example, here. This is because this fields here, they have a dependency. And this dependency is currently set to false. So if we look here in our advanced tab, which is just a screenshot of the content of the advanced tab here, here it says rename micrographs false. And if the rename micrographs is false, it means we don't need to provide a renaming prefix and suffix or some numbers to start with. And therefore, these are grayed out. If we would put this to true, it would be grayed in. Do we say enabled again? And you would need to fill it. So that means gray fields usually don't need to be filled out. So let's come to a more interesting topic, which is the global values. So usually when you go to some of the other tabs that are following, you see this use global value button, which is this big green button with a capital G in the center. And usually it means outside of the global tab. So for example, in motion, CTF, picking, extract, and so on, that if this button is green and then the input to this field is disabled, the color is changed to yellow, and the value is the same as in the respective field in the global tab. This has the advantage that you don't need to worry, that you can specify those settings here once, and they are available in the complete UI. But within this global tab here, it has a slightly different meaning because the value actually changes based on the situation. And let me tell you what kind of situations these are. So for example, the pixel size bin here, which is useful for super resolution data, because usually super resolution data is binned 2 times during the motion correction step. That means for all processors after the motion correction step, the pixel size is actually twice as high or doubled compared to before. So here you can specify in the global tab, you specify how much binning will be done during motion correction and the original pixel size, and it will calculate the bin pixel size automatically, so you don't need to worry about it. Same for like the box size. You specify your protein radius, and it automatically calculates the box size to be 3 times of the protein radius, and then it checks inside of a lookup table for optimized or optimal box sizes, which of those values is the closest, and will set up this automatically. Or if it checks for how many GPUs you want to use, it checks NVIDIA SMI output to see how many are available and how many memory is actually used. So when that means it does a lot of thinking for you as well, especially with this pixel size bin, is if you use, for example, the CTF find movie mode, then there's another switch that is actually needed, and it will do all this work for you, which is highly appreciated by our users in the facility. Now let me tell you about something more complicated, or at least it looks the most terrifying, and this is the notification tab. So you see a bunch of settings here, which might be like, what the hell, but it's actually not that scary. So let me break this down for you. So here, a number of values. You have the setting number of values used for median. So this is set to 5 by default, and this means that it will calculate the median for every value of the last X, in this case 5 values. So, and then you can specify for every output parameter, you can specify a valid range. In this case, the valid range is from -infinity to infinity. And this means is if the median of the last 5 values is outside of the specified valid range, in this case -infinity to infinity, then throw a warning, because there might be something wrong with the subsequent data collection and you want to know this as soon as possible. That means one outlier is not too troublesome, it always happens, but if they appear more often, it should throw a warning. So And if you can also use this to skip certain micrographs or remove them from the pipeline. So if a value, in this case not the median but the actual value, is outside of the specified valid range, in this case minus infinity to infinity, which means the complete range of possible scenarios, then please skip this image. But you can also say here, I don't want any motion or don't want any movies or micrographs that have an overall drift of more than 10 pixels. So this would definitely shrink down your data set considerably. So after you set up those, you need to decide what kind of software you want to use inside of the pipeline. So for example here, for motion correction, you have several options. You can either use Motion Core 2 or Unblur. And TranSPHIRE is designed so that it doesn't matter which program is used, it produces the same output, so that it's you can interchange them in any way you want. Same for CTF estimation. And you can also decide if you want to delete your original data, which might be beneficial for data collections live at the microscope, because sometimes, or most of the time, the data, the space on the actual hard drive is limited. So if you want to collect data for a week, you need to delete the data from the original microscope in order to not run out of disk space. So after the data is imported, which means copied physically from the camera computer to the local machine, you can either delete the data or you don't delete the data, or instead of actually copying the data, you just create a symlink, which is very useful for the just stack option. So what kind of programs are available? I see I have a typo here. So this should be, of course, motion correction for Motion Core 2 and Unblur. But we provide a support for Motion Core 2 and Unblur for motion correction, CETA, CTF-Finder, GCTF for CTF estimation, Cryolo for particle picking, Cinderella for 2D class selection, GPU Isaac for 2D class classification, Viper for ab initio 3D reconstruction, and Meridian for our 3D refinement. And so this GPU Isaac has been basically designed to run live next to the microscope within this TranSPHIRE pipeline, and it has the advantage that it has a very that the sorting capabilities are very high, so it produces more pure classes than other classifiers, because the group size is quite low, or because of the design. So the GPU Isaac basically enabled the TranSPHIRE pipeline to run the way it does right now. And it was developed by Fabian Schönfeld of our lab. So I won't go into every detail for every step here. Basically, you follow all the settings here. You stick to the main tab, or you might want to check out the advanced and rare tabs to see what kind of options are available, but usually you can keep them out of the way, like this way. But I would like to talk about the Auto 3D step, because it's a bit special. It needs a SPHIRE submission template, which can be downloaded from our website. And it has a few if conditions. For example, the input volume is optional in this case. If it's provided, no ab initio reconstruction with Viper is run, but this input volume is used. At the same time, if you don't provide this, then it will use Viper to create an ab initio reconstruction from your model. So if you do, for example, ligand screening, and you know how your particle looks like, but you just added some small molecules, then you might want to provide an input volume, because it's safer. And another big big thing here is that this job can either run on the local machine or on a different machine, which is accessible via SSH. So you can send the data, for example, we do it here, we send the data live to our cluster, and we say here, yes, we want to use SSH to submit our script here to our local queue on the cluster. And then the cluster will, which has much more computing power, will do the heavy work of 3D refinement for us. And yeah, and the output can be read by TranSPHIRE again because it's accessible via the mount point. Yes, so once everything is set up, you press the start button and you see all the metrics that are collected from every program. So here on the left, for example, you see the power spectrum of the data, you see the image itself, you see here some drift plot for this specific micrograph here, but you also have statistics about the complete overview here. So you here have an histogram of the overall drift, for example. Of course, it would be more impressive if there would be more than 14 images. But you can see the drift per micrograph. You can, or for every micrograph, you can see the average drift, the median drift, and this for every metric available for motion correction, CTF estimation, particle picking. So you can see everything at the same time. You see live all the class averages, picked images. So it's very useful to evaluate that, does this data acquisition go somewhere, or do I need to change some settings to make it more optimal and to get the most out of it. So this is how to use TranSPHIRE and what are the outputs. So of course, the outputs are all the files that the single individual programs produce. But this also means, because we are on Cryolo and Cinderella and Isaac, that all those outputs are usually available in the SPHIRE format. But especially for up to up to particle picking, those are also available in the Reliant format. So you can either import, so you can directly, it will create a particle CTF micrograph star file, for example, which can be imported into the Reliant pipeline. It will create a motion core star file, which can also be used for particle polishing directly, because I kind of copied the mechanism to create the particle polishing metastar files after successful motion correction was running, and those metastar files are created, so you can immediately start polishing after you successfully got a high resolution 3D reconstruction. And even though the outputs are available in the SPHIRE format, SPHIRE also offers the tools to convert the SPHIRE format into the Reliant format itself. So if you like the particle statics that you got after 2D classification, it's just one command away from importing it into your Reliant pipeline, or use it directly into the SPHIRE format. Or not only the Reliant pipeline, but the star format is actually readable by a lot of a bunch of software solutions in the field. So now that you know how it works and how to use it, I would like to emphasize one step of the TranSPHIRE pipeline, which is the feedback loop that we recently introduced. And this is basically working because our 2D clustering with GPU Isaac is first fast and reliable. Because the idea is that you don't say I want 200 classes, but I want like 100 images per class, and therefore one class cannot get so big that it sucks up basically all the particles from other classes, but it evenly distributes the classes, and therefore the classes itself are quite pure. So how does it work? So first we get available micrographs. Those are produced live at the microscope and are fed into the pipeline itself. Then Cryolo, in this case, picks those particles and provides the coordinates to the particle extraction command. This command extracts the particles and waits for a certain amount of particles to be accumulated. In most of the cases, it would be like 20,000 particles maybe. Then once this threshold is reached, those particles are fed into the 2D clustering GPU ISAC computation, and the resulting class averages are automatically selected by Cinderella to produce a good and a bad stack of class averages. The good class averages are, inside of the good class averages, there is the member information stored of the respective particles, and the respective particles have the coordinates stored from which they were extracted from. So this means we can extract the box files from the good particles and use this to retrain the Cryolo model that has been used for picking. And this new model is then used on not necessarily the same data, but on the new incoming data to repick again. And this feedback loop, how we call it, is executed in the default case 5 times, because this seems to lead to very good results. And after this 5 times is done, the final model is extracted and saved on disk. And then all the micrographs available up to this point are repicked and re-extracted and 2D clustered and 2D class selected, and there is the output particle stacks are accumulated on the disk, and then 3D refinement or ab initio reconstruction can run on those output stacks. So you might now see that this is kind of dependent, that the 2D class selection works as intended, so that it can ideally separate good and bad groups of particles. So in order to assure that, the TranSPHIRE offers a built-in Cinderella retraining tool. So once you stop your session, because otherwise it's hard to make sure that the GPU is not used twice. So you need to stop your session and click on the retrain tab. So once the retrain tab is opened, it will show you its current so it shows you, okay, Cinderella said those are good, those are bad. And either you agree with the result or you want to fine tune it so that it actually matches your result, because not every data set is as another one. So in this case, I said, okay, these are actually good particles. Those are not really bad, but I don't want them in my training. And those are bad particles here. This is just an example. Usually I would also put those here to the bad category, because here you can see the mask is cutting very harsh inside of those. And once you made this selection here, you click on retrain, and it will retrain automatically on those good and bad class averages. With afterwards, it will repick with the threshold provided in the lower right corner and present you the results in a new window, and you can check, okay, do I like this result or do I need to fine tune again? So this is an iterative approach until and in the end you get hopefully a satisfying result, and you can click on set, click on start, click on redo feedback, and once you clicked on redo feedback, it will redo all the feedback steps again, but now you're sure that the Cinderella model works as intended and gives you the best possible outcome. And with this feedback loop, we made some experiments. For example, here we have a TRPC4 channel. And what we did is we made a really crappy initial pig model. So here we have a micrograph, and the pigs are awfully off, as you can see. And after 5 feedback rounds, the model, without any user user interference, this feedback loop was able to recover almost every pig perfectly. So this was very, very impressive. And as you can see here from this graph, this already happened after like the 5th feedback round, and it gave the best results. So the Cryolo toolkit, let's say, also provides a tool to evaluate the best picking threshold for your model. And this means after the first feedback round, we can automatically determine the best picking threshold for the set of best selected particles that we got after Cinderella 2D class selection. And this so that means we can go with a very non-conservative threshold of like 0.1, which means pick basically everything you find, so that we assure that we don't miss any rare views. And at a later stage, after the feedback itself will tell you, okay, we don't need 0.1, 0.257 is actually much better. And with this help, we could get live at the microscope, we could get resolution of 3.5 angstrom with this data set, which is actually pretty impressive, and only within a few hours after data collection started. Another example is if you don't want to, if you assume you have a good picking model, but you have different conformations that are clearly separatable by class averages. So here we have a data set which consists of the holotoxin pre-pore, which we don't want to pick in this case, and the TC holotoxin pore, which we actually want to have in our case. So what we did is we provided a Cinderella model which classifies the pore state as bad, the pre-pore state as bad, and the pore state as good. And it learned to not pick the pre-pore state in the beginning, or not at all, because they do look very similar, but it reduced the amount of bad particles in this case dramatically, which improves not only speed but also usually accuracy of 2D classification and refinement. And my final example is we also used it for helical specimens. So what we did is we trained a model on F-actin, which is basically straight lines, as you can see here in the upper left image. And it does not have too much in common with actually actin-myosin, with an actin-myosin sample, where you not only have the straight line, but it more looks like it has this Christmas tree shape. So these little arrows. And actually, in round 1, it did not pick too much. You see, you have some very small amount of particles, but after round 6 of the feedback loop, it was able to pick actually quite a lot. And when we reduced the picking threshold to 0.3, so from 0.1 to 0.3, it did not pick perfectly yet, but it picked enough so that we got a very good 4.4 angstrom reconstruction out of 38,000 particles, which is quite high for this amount of particles for a helical specimen using the SBGrid helical reconstruction pipeline. And it was definitely enough to identify a small molecule bound here to this actin molecule. So which is sometimes what you want. If you want to go, oh, I want a resolution where I can see if a ligand or a small molecule is bound or not. You might not want the 2 angstrom resolution, but the 4 angstrom might be sufficient if you have a reference structure at hand. And with that, I would like to thank you for your attention, and the whole Department 3 group of Stefan Rounder, which was basically the beta testers for my software. And of course, especially those 6 people marked with an arrow that led to the nice paper that we presented and the feedback loop and the idea to the feedback loop in general. And with that, thank you very much. Follow us on Twitter and here, and don't forget to subscribe and like on YouTube for the SB Consortium.
Thanks, Markus. That was a great talk. So we've got a couple of questions in the chat. So if anyone else has any more questions, feel free to send them in the chat and I'll read them out. So first question is there a function that allows users to rerun the pipeline in case they want to change some settings? Do you start from the beginning, or can you kind of fork off at some point?
Yes, so maybe I just I came to this point in the very end. So if you press start for the first time, it will just start. But once it has been started once, if you click the start button again, then a continue dialog window will open. And in this continue dialog window, there's a bunch of checkable buttons, which of all the jobs you want to rerun. For example, if you want to rerun the feedback pipeline, you click rerun feedback because you realize, my protein radius is way too small, this will never work, or that my pixel size was wrong or something. Or you can just redo motion correction. So, and it automatically detects dependencies. So if you rerun motion correction, for example, then of course the results of CTF estimation will be affected, the result of particle picking will be affected, and the chain goes down. So it will find dependencies and rerun those as well. I hope this answers the question.
So we have another question about the 2D classification and clustering. Could you comment on the changes in 2D clustering? It sounds like to switch from k-means to some other clustering algorithm. I guess that's in relation to Isaac. Yeah,
so actually, no, we did not change the clustering algorithm of Isaac itself. Isaac is still using k-means, but it was always an equal size k-mean approach, which means that you not only keep the number of classes constant, but it's actually more important to keep the number of members per class constant. And in this way, it allows to identify smaller groups within a larger population and do sorting of small conformational changes as well. Some maximum likelihood-based approaches, they have a problem sorting minor differences within a tightly or very similar cluster, which is less severe in the equal size k-mean situation. So the GPU Isaac version is basically just faster than the normal Isaac version.
Okay. Then there's a few questions that I think relate broadly to configuration and profiles or templates. So the first one is it's a hugely flexible pipeline with a lot of different options. Is there a way for a facility to make, say, particular templates where a lot of those options are either pre-filled or potentially just locked so users can't change them away from their default values?
Yes, so locking is not supported yet. It might be actually something that I write right now on my list. But yes, so maybe I switch to a slide here. So here there's this default settings button. And in this default settings button, when you click it, unfortunately I don't have a slide for this, it will basically open another dialog, which looks pretty similar to what you see here. And here you can pre-fill every setting you actually want, if you want, and you can also move it to either the main, advanced, or the rare tab. So like locking would mean for me, for example, move it to the rare tab, because as a user, you could communicate if you don't touch the rare tab, for example. And then here on the user side, you can save it with a specific name, and the user can then, when he starts a session, click here on, in our case, maybe Arctica pixel size of this with faceplate template, and 99% of all the settings are pre-filled and are moved to the rare tab. So only maybe the protein radius needs to be provided because it's a protein or sample dependent setting, but all the microscope related settings are already set up and kind of not locked, but hidden from the user.
Oh, that's cool. So you can essentially pre-build a recipe, and if not lock the variables, you can at least hide them away so users have to hunt for them.
Exactly. So every template is modifiable in the way where it is, so where the setting is visible and what the value should be.
Okay. We have a question on mounts, which you mentioned right at the beginning. Is there an option for, or is there support for S3 or object store mounts for the archiving or the processing? So if people want to archive their movies up to AWS or to Glacier or whatever.
So the mounting actually just works via, so it creates a mount point and then uses this output folder of the mount point. So that means you can either set up, so this mounting option, in our case, we kind of do the mounting ourselves. So you provide your username. We have passwordless mounting. So you just provide your username and the mount point is created for you and can be used. But you can also predefine mount points or with, for example, a fixed folder. So let's say you mounted and set up all your settings with another on the mount point so that it's available on your file system. You can create a mount point. This is mount point for some archiving, and say this is the path to this mount point, and then the user can just say, I want to use this one here, which is already pre-set up, because there might be more than one backup solution, for example, depending on the group maybe. So yes, I think it's possible.
Okay.
I hope this answers the question. If not, write me mail.
I think that answers another question we had, which was if facilities could pre-configure mount points for users similar to some other software which has kind of site definition files, but it sounds like that is possible.
Exactly, yeah.
Okay, great. That was the last question I have at the moment in the chat. So if anyone else has any questions, feel free to send them along now. Otherwise, I'd just like to thank Markus for a really interesting talk, and then quickly give a plug for our next webinar next week on November 3rd, where we have Vicky Hickman from the University of Leicester, who will be talking about CCP NMR. So changing pace to a slightly different structural technique. But yeah, thank you again, Markus. That was really interesting, and thank you all for listening.